Richter from Blekinge Institute of Technology in Sweden, and he will be talking about non-associative versions of Hilbert's basis theorem. So please, Johan, go ahead.
Thank you very much, and thank you to the organizers for the invitation. I hope you all can see the presentation I shared and that you can hear me and so on. Let me know if there's any problems. Yes, so I'm going to speak about non-associative versions of Hilbert's basis theorem. This is a joint work with Per Bäck. Well, it's published in Colloquium Mathematicum. I'll have a few references at the end, including the where this was published exactly. Some conventions in this talk. All rings are unital, but not necessarily associative, as can be expected from this seminar, and indeed from the title. So the definition of what it means for a ring to be Noetherian, it means that a ring is left Noetherian if every left ideal is finitely generated. And this is equivalent to requiring every increasing chain of left ideals to stabilize. So, okay, very well-known definition. But I just wanted really to note that there's no difference here between the associative case and the non-associative case. At least not in any of my work, when I don't think so. I haven't seen any reason to have a different definition in the non-associative case. And of course, there's the corresponding notion of right Noetherian rings as well. I mean, the original motivation came from algebraic geometry, I think. And if you have a set of polynomials and you want to study the set of common zeros of these polynomials, since the polynomial ring in n variables is Noetherian, we might as well assume that the set of polynomials is finite. So a nice concrete motivation, but Hilbert's basis theorem has been generalized to a considerable degree away from this setting. And yes, so I will talk about some such generalizations today. Here is what's usually known as the classical, here is what is usually called Hilbert's basis theorem. That if we have an associative left Noetherian ring, then the polynomial ring over this ring R is also left Noetherian. And equally, if the ring R is right Noetherian, then the polynomial ring over R is also right Noetherian. So this polynomial rings, even if R is non-commutative here, we assume or define this new element X to commute with everything in R. Yeah. So this is a classical theorem. It's been generalized in the sort of the associative setting before we come to the non-associative case. So to describe one such non-associative generalization of Hilbert's basis theorem, I'm going to describe the notion of Ure-extensions. So this is something that's maybe not so, maybe everything up to this point is very well known to everyone, but this might not be well known to quite a few people. So what's an Ure-extension? Well, if we start with an associative ring R, then we want an associative Ure-extension as well. Well, this is going to be a ring that is a superring of R, which is generated by the elements of R and a new element X, such that when we multiply X by R in that order, we get something that looks like this. Okay, so maybe we should focus here on the original name for Ure extensions were non-commutative polynomial rings. So the idea is that we have some sort of non-commutative polynomial ring in X. And when we take X times an element from the coefficient ring, we get a first-degree polynomial. So well, I mean, if we do that well, we must have some sort of function sigma and delta here, depending on R, that gives us the coefficient of this new first-degree polynomial. And it turns out that the conditions we want to require on sigma and delta are that sigma should be an endomorphism, and delta should satisfy two rules. So delta should be additive. Delta of R plus S is delta R plus delta S. And delta should satisfy this funny rule. Delta of RS is sigma R times delta S plus delta R times S. So this looks like some version of the Leibniz rule from derivations, except that we've inserted a sigma here. So this delta satisfying these conditions are called sigma derivations, generalizations of the concept of derivations. And why do we want these conditions? Well, with this definition, where I start with generators and relations, these are what's necessary to make every element of the Ure extension to be uniquely written as a sum of, as a linear combination, we might say, of powers of X. So there are other ways of starting where instead these conditions are necessary to make it associative or so on. But yeah. But anyway, case with these conditions, we get an associative ring with the powers of X as a basis, as a free left R module. And you can do it and you can do a version of the construction where you have the coefficients on the right instead, of course, but I'll always write them on the left. Some examples, well-known example, normal polynomial rings are examples of Ure extensions where the sigma is the identity function and the sigma derivation is the constant zero function. Another example, also well-known, is the Weyl algebras. I've written the first Weyl algebra here because it's this object. So you take a polynomial ring and then you do an Ure extension of the polynomial ring where the sigma is the identity map again and the delta is the normal derivation with respect to y. And then you get what is called the first Weyl algebra. So the algebra generated by x and y, where xy minus yx is equal to 1. So from quantum mechanics and differential equations and so on. Yeah, and actually the other Weyl algebras are then further Ure extensions of this. So the Ure extensions also appear in when you study universal enveloping algebras of Lie algebras. Some well-known examples are the Ure extensions. They appear in coding theory recently, so there's some applied connections, and yeah, they are quite interesting. And well, one can generalize Hilbert's basis theorem to Ure extensions. So the following, and this is a well-known generalization. So it's certainly not my work. I'll describe when we come to our work. So it says that if we have an associative left Noetherian ring, and we have sigma is an automorphism of R, and well, I'm assuming here also that delta is a sigma derivation, then the Ure extension is also left Noetherian. And similarly, if we start with our right Noetherian ring, then the Ure extension will be right Noetherian. Yeah, I mean, the proof is, not discuss proofs a lot, but I mean, it's a generalization of the normal proof of the Hilbert's basis theorem. It's easiest to prove the right case first and then pass to an opposite ring in the left case, it turns out. Yeah. Okay, so I mean, this would example, well, if you want an example, the first Weyl algebra is Noetherian by this field. So now we move into the non-associative case, because we want to generalize actually to the Hilbert's basis theorem to non-associative Ure extensions. And the concept of non-associative Ure extensions is something that we introduced earlier, so not in the article with Hilbert's basis theorem. It's something we had introduced earlier. But what's the idea here? Well, I mean, we sort of think about the construction. If we instead start with starting with an associative ring R, we could start with a non-associative ring R. Okay, we can still do the construction to get an URI extension. But maybe in this case, the conditions on sigma and delta we imposed before are not so interesting because we imposed them, I mean, in some sense, because of associativity, really. From starting from one point of view, you can impose them to get associative a ring. But I mean, we're not going to get an associative ring here anyway if we extend a non-associative ring. So maybe we should weaken the conditions on sigma and delta as well. So, and that is what we've suggested. So we suggested that a non-associative URI extension should be defined like this. We start with a non-associative ring R. We have additive maps, sigma and delta, such that sigma of 1 is 1 and delta of 1 is 0. So all rings were unital, so there certainly will be a 1. Okay. So, and then we are going to equip the polynomial ring. I mean, how do we define it sort of set theoretically? Well, I'm going to explain it like we take Rx. We can certainly define a polynomial ring over this non-associative ring R. And we're going to use that addition, but we're going to define a new multiplication to make our non-associative URI extension. And how do we do that? Well, we actually take a formula from the associative case for what happens when you multiply monomials like this and use that in the non-associative case as well. So the product of AXM and B, so I mean, we're going to start with the ring R and we're going to get polynomials in X in some sense, but they're going to be a very generalized form of polynomials, right? Non-associative and non-commutative. So the product of AXM and BXN is going to be a sum like this. So so maybe I should put a parenthesis here around in front of the power of X, because that multiplication will be done in just the ring R. Okay, every coefficient here in the sum will just have A multiplied on the left. That is easy. But then what do we do with B here? Well, every such expression pi mi of B is actually a sum in itself of different compositions of sigma and delta acting on B. So pi mi denotes the sum of all possible compositions of I copies of sigma and m minus I copies of delta. Yeah. So in any order. So it's a sum of many functions. M choose I functions, and you apply them all to B, and that's what you get here. Yeah. And and I mean, okay, so it's not an infinite sum because we also sort of define if I is larger than M, we define them to be 0. That doesn't follow directly from the definition. And yeah, so this is the formula from the associative case. I mean, we want to keep it because we still sort of want the multiplication to preserve the degree and so on. We want to keep a few polynomial-like properties. Otherwise, there's no connection to the polynomial case. And you can do this. You get this becomes a well-defined non-associative ring. And then you ask, well, can you prove Hilbert's basis theorem for that? Yes. So what Pierre and I did in an earlier article, not the latest article, the one I mentioned in colloquium, was that we considered the case where we start with a non-associative ring, but we insist anyway that sigma should be an automorphism and delta a sigma derivation on R. Then, if R is right Noetherian or left Noetherian, then the URI extension will similarly be right Noetherian or left noetherian. Yeah. And in this article, actually, we discuss a homo-associative case, we call it. So for those of you familiar with homo-associative algebras, there's some discussion of that case in that article as well. And well, let's give an example of this theorem. I actually have two examples. I'm not sure how interesting they are, but yeah, I'll give them anyway. So one example, well, if you have a unital non-associative algebra over a field of characteristic different from 2, one can turn it into a Jordan algebra, or one can construct a Jordan algebra from A by using the Jordan product, which is well, the average of the A times B and B times A, you might say. And yeah, so this becomes a Jordan algebra. So it's a commutative algebra where any two elements satisfy an n identity like this. Okay, I don't know much about Jordan algebras, but you don't need to know that for this example. So, okay, so how can we do a more concrete example, perhaps? Well, let's take the quaternions and take a specific automorphism on them given by this sigma here. Any automorphism on the quaternions is also an automorphism on the Jordan version of the quaternions. Okay, so yeah, and then we can take delta to be the zero map. That is certainly a sigma derivation. So we can construct an Ure extension of this of the quaternion, I mean of the Jordan quaternions, or whatever you should call them. And this will be then be noetherian because obviously sort of the Jordan quaternions are noetherian. Yeah, I have another example if you have no question. So this is quite a long text here, but the idea is a sort of a an Octonian version of the Weil algebra is really the only idea. So maybe that is all I should say. I mean, yeah, so basically we start with a polynomial ring over the octonions, and we can define, yeah, I mean, we take the identity map as for sigma, that is certainly an automorphism, and we take for delta, we take, I mean, something that acts like a normal derivation, acts like a normal polynomial derivation, and then you can use these to form an Octonian Weil algebra or octionic Weil algebra I've written here. And yeah, this will also be noetherian by the previous field. Okay. But so that was previous work, you might say. Let's move closer to our newest article. So we in the previous theorem, the assumptions on sigma and delta mirrored the associative case. Well, but in the definition of the non-associative Ure extension, we did not have such conditions on sigma and delta. So what happens if we allow sigma and delta to be more general? Well, then we can prove the following theorem, which is in the colloquium article. So let R be a unital non-associative ring with an additive bijection sigma, such that the sigma 1 is 1. This is only that respects 1 only means that sigma 1 is 1. And we have an additive map delta such that delta 1 is 0. If R is right noetherian, then so is the non-associative Ure extension. So the proof is it's similar to the non-associative case. You just sort of have to check, well, do we use the associativity anywhere? And yeah, and as I said, in the associative case, one can then pass to the left case by using the opposite ring, which does require associativity to become a problem. Okay, I have an example of this theorem as well. So, I mean, in some sense, it's quite a general construction, these non-associative Ure extensions. So it's quite easy in some sense to construct examples. I'm not saying these examples are super interesting in and of themselves, but yeah. Well, here is an example anyway, or class of examples. So we can take any bijection of the natural numbers such that f of 0 is 0. And we take a field K, and we take as our ring R the polynomial ring in Y over K. And then we want an additive bijection on this R. So we use this F in the following way by saying that sigma of R times Ym is R times Y to the power F of n. Okay, and I mean, then we extend additively to all the polynomials and so on. We can let delta be the ordinary derivative on R. So, I mean, that's really interesting. There's no real connection between sigma and delta, but that's not really required by the theorem. Yeah, I mean, sigma of 1 is 1, delta 1 is 0. So by the previous theorem, these Ure extensions we get in this way are Brighton-filled. Okay, now I've said right Noetherian. What about left Noetherianness? Well, I don't actually know what happens in that example, but I do know that in general, a left version of Hilbert spaces theorem does not hold in a non-associative case. So we have a counterexample where R is a polynomial ring over a field, but this, so definitely, I mean, it's even associative, it's definitely Noetherian by the Hilbert spaces theorem, but this is not necessary. This Ure extension is not left Noetherian. So I thought I'd describe that counterexample. So this is an important slide for that counterexample. So I take R to be a polynomial ring in 2 variables. Okay, did I say 1 variable before? Well, I meant 2 variables. So a polynomial ring over a field at least. Maybe that was all I said. And we will define an additive bijection sigma such that sigma of 1 is 1, and sigma acting on binomials like this, so yi times zj, is equal to y to the power 2i times zj, if I is greater than 0. Okay, then we're going to create the Ure extension with this sigma and delta 0, call it t. The element y will generate some ideal in R, of course, in the polynomial ring. And then we will describe an ideal in T, which is not finitely generated as a left ideal. So this ideal or left ideal in T, well, it's the set of elements where all coefficients come from this ideal I. So, I mean, essentially, all coefficient here should contain a factor of y. That should be what it is, right? Yeah, so I'm going to claim that this ideal will not be finitely generated. Okay, so the next slide, I'm going to have the details of the constructions of this sigma, which I probably won't go through in detail, because it's somehow obvious, right, that there must be an additive bijection that satisfies this. I mean, I can make this definition, and then I have infinitely many binomials left to take care of the remaining cases, and I can define it on on every sort of binomial, I can define it independently of any other binomial and still get an additive bijection in the end. But if the details are given here using, yeah, I don't think it becomes easier to understand by me trying to go over this, but it's certainly possible to do using some bijections of the natural numbers and so on. Okay, so suppose we have this sigma defined. What are we going to do then? Well, I mean, we define this Ure extension, which we then can do. And then we think about what happens when we apply this sigma to the ideal I. I mean, if the sigma acts on an element from the ideal I that was generated by y. Well, I claim that it's mapped to the ideal generated by y squared. Because every time we have y, a factor of y is going to be replaced by y squared, right? So this so this is what happens. Sigma maps the ideal I to a smaller ideal. Okay. And then I define this J ideal in T again, and I'm going to claim, which is not finitely generated as a left ideal. And why is it not finitely generated? Well, maybe it's obvious, but let's go through an argument anyway. Suppose that it were finitely generated by some elements, P1, P2, up to Pn. Well, then they are finitely many, so they're going to have a maximal degree in X. Okay, and we let M be the maximal degree in X of all these generators. And well, this element, y times x to the power m plus 1, this is certainly in the ideal J. Every coefficient here, it's only one coefficient that is non-zero, and it's certainly in the ideal I. It's certainly in the ideal generated by y, so this should be in the ideal J in the Ore extension. Okay, but essentially this is impossible because, well, these do not have degree m plus, none of these have degree m plus 1 on their own. So to get to degree m plus 1, we would have to multiply by x. From the left, since we're talking about the left ideal. But every time we multiply by x from the left, all the coefficients are suddenly going to have a factor of y squared, not just y. And and then it's not impossible. Then it's not possible to get this element. All the terms. Since it's non-associative here, we can't just say that we have it generated like this, but it's some sort of can also generate it like this or so on. But in any case, if in any of these sums we have an element of degree larger than m, then the coefficient is going to be in the ideal generated by y squared. So it's not possible to get any sum of these terms to be this. So that's the argument. And I think this example is sort of quite interesting because, you want to generalize theorems. And so it's interesting that you can generalize the Reitner theorem to the non-associative case. But it's somehow also interesting that what does not pass to the new situation. So that the left case, which sort of, in the associative case, you do not sort of think of the right and left case separately often. But here it really turns out to make a difference. I think this is this distinction is sort of the most interesting result we have in our article. Okay. If there are no questions, I'm going to move on to some other versions of Hilbert's basis theorem that we proved for in non-associative rings. So it's not only Ore extensions we worked with in this article, we also worked with some related structures. So this is what I say here. We've also proved some versions of Hilbert's basis theorem for other types of non-associative rings. So one type of ring we studied, well, I'm going to define it in several slides because it's a generalization of a generalization and so on. So a Laurent polynomial ring, where we start with an associative ring. Well, this is like a polynomial ring, except we allow negative powers of x as well. And x is still a central element. And you could say it's the localization of the normal polynomial ring with respect to the powers of x. Okay, so how can you generalize this? Well, there's a generalization which is similar to the Ore extensions of the Laurent polynomial rings, which are called skew Laurent polynomial rings. So the idea here is that we have sort of the same elements as in the ordinary Laurent polynomial ring, and it's the same structure as a left R module. But when we multiply monomials in this ring, we have this rule. So we insert some function sigma here. that AXM times BXM is A sigma M of B times XM plus M. So, I mean, this is, well, if you took the overextension case and set delta to 0, this complicated rule I wrote before would simplify to this. So in the Laurent case, you do not have any delta, you might say. That's the difference between overextensions, and instead we can then allow negative powers. Yeah. So in the associative case, when we want the scalar ring to also be associative, we want sigma to be an automorphism. Okay. But if we want a non-associative scalar polynomial ring, I mean, we can just sort of relax the condition of on being an automorphism and say that sigma should be a bijection and that sigma 1 is 1. Yeah, so I mean, this phrasing here is we said we define the non-associative overextensions in this way. I mean, it should really be non-associative scalar polynomial rings. That's good. So by allowing R to be non-associative and only saying that sigma is a bijection, such as sigma 1 is 1. Yeah, and we can prove a version of Hilbert's basis theorem for these non-associative scalar polynomial rings as well. So if we have a non-associative ring with an additive bijection, such as sigma 1 is 1, then if R is left or right Noetherian, then so is the non-associative scalar polynomial ring. Yeah, so this is a generalization of an associative result for associative scalar polynomial rings. And this proof is, well, we give a proof for an adaptation of a proof for group-graded rings by Bell. So it's not the same really type of proof as for the overextensions. Yeah. And in this case, there's no left or right symmetry. Yeah, and I mean, there is some sort of connection, just not sort of the similarly in definition between the scalar and the overextension case, because, I mean, in any non-associative scalar polynomial ring, there is an overextension sitting as a subring. Yeah. So we, then you can relate the ideals of sort of the overring and the subring. And you can do this to give a sort of an alternative proof for the right case of Hilbert's basis theorem for scalar polynomial rings, but yeah, not in left case, obviously. Yeah. So, but this ideal that connection between the ideals obviously does not allow us to prove Hilbert's basis theorem for overextensions in the left case. Yeah. So we also, I'm coming actually towards the end of my talk, but we have two further structures we also looked at. So we define non-associative skew power series rings and non-associative skew Laurent series rings. So what's non-associative skew power series ring? Well, okay, so there are generalization in 2 steps of power series rings. Where power series rings we probably encountered sort of set of infinite formal sums where the coefficients are from R and we only allow non-negative powers of X. Okay, one can sort of using only sigma, no delta, one can do sort of twist the multiplication rule in the same way as for the skew Laurent rings, and then get a skew power series ring. Okay, and then one can ask, well, can we make it a non-associative structure? Again, yes, you absolutely can. If you only require that sigma is a additive bijection, such as sigma 1 is 1, then you can define a non-associative skew power series ring. Okay, and what's a non-associative skew Laurent series ring? Well, okay, so we allow negative power. In this version, we allow negative powers of X also. But so for any element, there's only going to be finitely many negative powers of X. So, I mean, this is, I mean, if you encounter this sort of Laurent series in complex analysis, they're allowed to have infinitely many negative powers of X, but algebraically, that's not so good. So we only now finitely many, for each element, there are only finitely many negative powers of x of L in the non-associative scalar series ring. Yeah, and in general here, I mean, sigma is just an additive bijection, such as sigma 1 is 1 as well. But unfortunately, in this theorem we prove here, we do add one condition compared to our previous theorem. So we say, let R be an associative ring with additive bijection sigma such that sigma 1 is 1. If R is right Noetherian, then so is the non-associative skew power series ring and the non-associative skew Laurent series ring. So it's like, so maybe it's like this. This is weaker than some of the previous theorems in two ways. So we only prove the right case, and we start with an associative ring. Even if the construction does not result in an associative ring, because we're not requiring this to be an automorphism, we do still start with an associative ring. And I mean, this is for a certain step in the proof to work. And so we do have two questions. Can one generalize this theorem to start with a non-associative ring? Can one prove a left version of these theorems? We don't know. So if anyone can answer that, please tell me. Yeah, and that's actually all I have to say, if you don't have any questions. And this is sort of some list of references, a very sparse list of references, but yeah, here's the sort of the paper I was actually talking about today, maybe. This is some previous stuff that I also mentioned. This is a good reference for a lot of these Hilbert spaces theorem for the associative case. And this is a proof by Bell we generalized. And this is where UR extensions were first defined.
Okay, thank you very much for the presentation, Johan. Are there questions or remarks?
Could I give applications? That's tricky. I mean, there are examples. So I can give examples. I gave some. I could probably construct more, not on maybe standing here. But applications, that's trickier. I can't say that I've sort of applied it to any outstanding problem that we now solved or anything like that. No, I can't claim that.
Okay, maybe I have a really nasty question for you. Sorry, but do you have any feeling for why it's sort of associativity that makes this difference between left and right and not commutativity that I would expect at least? Or do you have any feeling why?
Any feeling? No, not in a, I mean, I've seen the proofs and I understand the proofs when I read them, but I mean, some intuitive feeling, no, not really. I mean, in the construction of UR extensions, there is some sort, even in the sort of non-associative case, there is some sort of associativity built in because, I mean, this X, it's not going to be a central element. It's not going to even be in sort of associate with everything, but it's going to be some sort of in the right associator or something like that. And I think it's somehow connected to that, yeah, I mean, it's somehow, how about Lie co-algebras? I don't know if there's connection to this setting, actually. Could you elaborate on the idea? There was a question in chat. What about Lie co-algebras? I'm not aware of any connection to this. A Hilbert theorem? Yeah, I mean, doesn't satisfy. I mean, we do want unitality usually for when we have Hilbert spaces theorem. Do Lie co-algebras have unitality or anything similar? I think, I mean, when we looked at the various forms of generalizations. We actually have an article, a different article, sort of generalizing in different direction with like two other co-authors that's recently been published in Impact. Co-unitary, okay, so maybe there is something to prove in that case. I haven't looked at it, but it's maybe some idea that I'll write down. But we have, at least what we have done, we have found that some sort of unitality condition is what we want when we do hypostasis.
Okay, if there are no further questions, I guess we'll thank the speaker and conclude today's seminar. Thank you.